Since we've got these sum and difference identities, we're going to be able to use these to come up with some other very useful identities that I'm going to show you now. And these are kind of, well, the first ones that I'm going to show you are almost sort of just like special cases where we're looking at a sum of two angles that are actually the same angle. So let me demonstrate exactly what I mean by this. Let us suppose that I want to know what is the cosine of 2 times some angle alpha. Well, this is actually the cosine of alpha plus alpha, because of course alpha plus alpha is 2 alpha. Well, what does that come out to be? That is going to come out to be, if I go back and I use the sum identity that we had, or as we said in the last video, that's also known as one of Ptolemy's identities, I can rewrite this cosine of alpha plus alpha as cosine alpha times cosine alpha minus sine alpha sine alpha. But that's really, since these are the same angle here, this is cosine alpha, this is cosine alpha, so this is really cosine squared alpha, and this is really minus sine squared alpha. So in summary, what I have found here is that the cosine of 2 alpha is equal to cosine squared alpha minus sine squared alpha. Now, there's actually a couple of different ways that I could write this if I wanted to as well, all of which are very, very useful in this particular instance. So I want to show you guys how I can rewrite this using the Pythagorean identity to get two other forms. But first of all, this is one of the double angle identities. We're going to see more in a moment, but first let's see how we could rewrite this thing. What I want to remember here is that sine squared alpha plus cos squared alpha is equal to 1. This means that I could rewrite cosine squared alpha is equal to 1 minus sine squared alpha. So that means this right-hand side could be rewritten as 1 minus sine squared alpha minus sine squared alpha. So this part here that I just put in the world's weirdest looking parentheses, this part here comes from the cosine squared, and this minus sine squared, this one just comes from the fact that we have a minus sine squared in the original expression here. But minus sine squared minus another sine squared is really just minus 2 sine squared. And so what I get here is that this can also be thought of as 1 minus 2 sine squared alpha. So this is another way of thinking about the double angle formula for the cosine. One more thing that I can do if I want to rewrite this thing is I could, instead of saying cosine, whoops, that should have a cosine squared alpha. I dropped my alpha on there. I'm sorry about that. One more thing that I should be able to do is to rewrite sine squared in terms of cosine squared. So I could say sine squared alpha is actually 1 minus cosine squared alpha. Well, that means this original expression cosine squared alpha minus sine squared alpha, this is going to become cosine squared alpha minus, let's substitute this expression down here. We would have 1 minus cosine squared alpha, all in parentheses, which means this negative is going to distribute, and it's going to give me 2 cosine squared alpha minus 1. So this is yet a third form of the double angle formula for the cosine. So as you can see, we didn't have to make any kind of geometric arguments here in order to get the double angle formula. all we had to do was to go back and think about the sum identity for cosine. Well, I erased it. Why am I pointing at this? This is a Pythagorean identity. We just had to go back and think about the sum identity for the cosine function, and that really gave us this for free. Now, I can pull the same trick for the sine function. So let's take a quick look at how that works out. After I get some space on the board. And after I drop my pen. All right. Everything is under control again. So let's suppose that I want to find what is the sine of 2 alpha. Well, if I go back to my sum identity, I can say that this is actually equal to the sine of alpha times the cosine of alpha plus the cosine of alpha times the sine of alpha. Well, let's take a look at this. These are actually the same thing. It's just that the product is written in a different form. I've just switched the cosine and the sine. So look at this expression. It's sine alpha, cosine alpha. This expression is cosine alpha, sine alpha. So this actually comes out to be 2 sine alpha, cosine alpha. And we're all set. Now, for sine, there's really only one form of the double angle identity that's worth thinking about, and it's this one. I mean, as with any trig thing, you can rewrite it as much as you want to using the Pythagorean identity and stuff, but in this case, yeah, this is really the form that you're going to want to stick with. There's not much that you can do to change that around. If you wanted to, you could also work this out for the tangent function. And probably the easiest thing to do to get the tangent is really just to take the identities for sine and cosine, put them together, and see what they simplify out to. I'm just going to tell you guys the answer because it's not like seeing this is anything particularly new. The tangent of 2 times alpha is equal to 2 tangent alpha divided by 1 minus tan squared alpha. Okay, so we have these new identities. So what else can we say here? Well, double angle formulas turn out to be nice, but it turns out that it would be much more interesting to ask ourselves, what would we get if we wanted to find the values for half of an angle? In other words, what if instead of asking myself, what is the sine of 2 alpha, what if I asked myself instead, what is sine of 1/2 theta? Well, the way that I'm going to work this out is I'm going to say, okay, let's think about what this is. And while we're at it, we also would really like to know what is the cosine of 1/2 theta. These would be very interesting questions to answer. And we'll talk in a minute about why they would be so interesting. But first of all, let's think about how we could get these. Well, the way that we're going to get these is we're going to use the identity that we had, and unfortunately I erased it, because of course I wrote things in this order instead of the other order, but we want to use the identity involving cosines. So remember that the cosine of 2 alpha is equal to 2 cosine squared alpha minus 1, and it is also equal to 1 minus 2 sine squared alpha. So, what does this mean for our particular situation up here? Well, this would mean that the sine of theta is equal to 2 cosine squared, I'm sorry, not the sine of theta. What am I writing down here? The cosine of theta Yes, sorry, I wrote sine, but I was trying to write cosine. I just looked back at the wrong thing for a moment and got sine in my head. The cosine of theta is going to be equal to 2 cosine squared 1/2 theta minus 1. So what have I done here? Really, what I am doing here is I am saying, let's take alpha to actually be equal to 1/2 theta. If alpha were equal to 1/2 theta, then 2 alpha would just be theta itself. Okay, so really, we're just taking alpha equals 1/2 theta, and we're plugging it into this formula. Now, what's going to happen here is I can now solve for this cosine squared of 1/2 theta. And when I do that, I get cosine squared 1/2 theta is equal to cosine theta plus 1 all divided by 2. And if I want to solve for this thing, then I can say that the cosine of 1/2 theta is equal to plus or minus the square root of cosine theta plus 1 all divided by 2. If I want to know the plus or minus information, all I need to do at that point is to ask myself, what quadrant would 1/2 theta find itself in? Once I know what quadrant 1/2 theta is in, well, that's going to tell me the rest of this information that I need. It tells me whether it's positive or negative, because remember, cosine is positive in quadrants 1 and 4. Hopefully you guys remember that by this point. Cosine is negative in quadrants 2 and 3. So I can figure out whether I want to take the positive or the negative square root. Now, another way of writing this would be to say that the cosine of theta is equal to plus or minus the square root of cosine 2 theta plus 1 all divided by 2. So that's just a slightly different way of writing out the same formula, which is sometimes more useful. I wouldn't necessarily say it is always more useful or less useful, but it's another way of thinking about it. Okay, now, we figured out an expression for the cosine with the half angle, but what can we do for the sine? Well, it turns out that sine is also something we can get by using one of these identities here. So I'm afraid, unfortunately, the way I wrote this on the blackboard makes things look a little confusing here, but I'm now going to use this identity to do the same trick and get an expression for the half angle identity involving sine. So if alpha is 1/2 theta, then what we really have here is that the cosine of theta is equal to 1 minus sine squared 1/2 theta. I'm doing the same substitution here of alpha is equal to 1/2 theta, okay? Nothing really different than what we just did a minute ago. Notice, though, even though I'm working towards a formula involving sine, I still get a cosine on the left-hand side. So what's changed is what I put on the right-hand side involving the 1/2 theta. Before we had the cosine squared coming from this guy. Now we're using the sine squared coming out of this guy. From here on out, everything is pretty similar to what we said before. So we're going to get sine squared of 1/2 theta is going to be equal to 1 minus cosine theta divided by 2. So that just comes from solving for sine squared 1/2 theta here, pretty much like we did before. And that tells me that the sine of 1/2 theta is equal to plus or minus the square root of 1 minus cosine theta divided by 2. So notice that the half angle formulas both end up involving cosine. It doesn't matter if we're working with sine or with cosine to start with, we end up writing it in terms of cosines. Again, if you wanted to, you could rewrite this as the sine of theta is equal to plus or minus the square root of 1 minus cosine 2 theta divided by 2, if you wanted to. So these identities are known as the half angle identities. You can also use all of this to work out a formula for the tangent, and the formula that you end up with for tangent is that the tangent of theta over 2 is equal to sine theta divided by 1 plus cosine theta, which can also be written as 1 minus cosine theta divided by sine theta. I will leave it to you guys to work out that these are actually equal to each other if you are interested in figuring that out. I mean, it's the same kind of identity proof that we've done before. Nothing particularly new here, just, kind of rewriting things and showing that these two sides are equal. And you get this identity to start with by just taking the ratio of the sine and cosine identities that we had. Okay, so why are half-angle identities so nice? Well, the reason that half-angle identities are so nice and so valuable and useful is because they are now going to allow us to find exact values for trig functions or things involving trig functions that we would not have been able to find before. So I'm going to leave these identities up for a moment and just give you guys some demonstrations of what I mean by this. Okay, so let's suppose that I want to find an exact value for sine of pi over 12. Well, this is a problem if I just look back at my unit circle, because there are no pi over 12s on there. Now, there is a way that I could do this by using the difference formula. So I think we did work this out as an example. We showed that you could actually do this by writing pi over 12 as pi over 3 minus pi over 4. And that works, but I want to show you a much easier way using the half angle identities. Well, in order to do that, I can think here that theta is equal to pi over 12. So 2 theta is equal to pi over 6. And that's nice because I actually know what to do with trig functions. I can evaluate those at pi over 6. Those are like fundamental angles on our unit circle that we just know. So if I take this formula for sine, I can say the sine of pi over 12 is equal to plus or minus the square root of 1 minus cosine pi over 6 divided by 2. Now, should I take the plus or the minus here? Think about that for a minute. If you're having trouble figuring that out, ask yourself, what quadrant is pi over 12 in? It's in quadrant 1, right? And sine is plus or negative, positive or negative in quadrant 1. Hopefully you guys are remembering, in quadrant 1, all the trig functions are positive, so we want to take the plus answer. Okay, so this is going to become the square root of 1 minus, and then what is cosine of pi over 6? Well, that's going to be square root 3 over 2. All divided by 2. And we can be fancy if we want to and rewrite this a little bit, I suppose. So we can write this as the square root of 2 minus the square root of 3, all divided by 4. Right, because this is 1/2, this is minus square root 3 over 4. So that becomes 2 over 4 minus square root 3 over 4. And that gives me this. Okay, now, you can go back if you want to and figure this out using the difference identity, but that is not going to necessarily really be the easiest way of doing it, in my opinion anyway. I think this is the easier approach to this kind of a problem. Now, One of the nice things here is that you can iterate this method. In other words, you can use this method repeatedly. So let's take a look at this example, which would be very difficult to do if we just had the sum and difference identities, but it turns out to be, I won't say easy, it's not necessarily easy, but it's kind of straightforward at the very least to do it using these half-angle identities. Okay, so let's ask the same question, except I want to find this time the sine of pi over 24. Now, off the top of my head, I don't know how to write pi over 24 as a sum or a difference of angles that I know. You know, angles where we know the trig functions, things like pi over 4, pi over 3, pi over 6. Off the top of my head, in fact, I don't really think you can. You could use the sum and the difference identities iteratively to do this, but it would be kind of a pain. It turns out to be fairly straightforward if we just start mucking around with the half-angle identities here. So what do we do? Well, what I'm going to do is I'm going to say, well, the sine of pi over 24 is equal to plus or minus the square root of 1 minus cosine pi over 12, all divided by 2. Okay. Now, pi over 24 is in quadrant 1, so we want to take the positive square root, just like in the previous example. Well, that's fine. But now we have the problem that we don't know what is cosine of pi over 12. Does that mean we are stuck, though? Take a minute and think about this. What could I do to figure this out? Well, the answer is, to figure this one out, I can just apply the cosine half-angle identity. So I can say the cosine of pi over 12 is equal to plus or minus the square root of cosine pi over, whoops, why did I write a pi over 2? Cosine of pi over 6 plus 1 divided by 2. Now, pi over 12 is quadrant 1. We take the positive square root here, and this comes out to be square root of. Now, cosine pi over 6, we said this a minute ago in the previous example. This is actually the square root of 3 over 2 plus 1, all divided by 2. And so this is going to come out to be, let's see, so this is square root 3 over 4 plus 2 over 4. So this is going to be square root 3 plus 2, all divided by 4. Okay, so this thing, this original thing, I can take this and I can plug this in for cosine pi over 12. And I get the square root of 1 minus square root of square root 3 plus 2, all divided by 4. And then the whole thing is divided by 2. Now, this is a mess of nested square roots, but it is an exact value for these things, okay? And that's all that we really need, right? I mean, if we're just interested in an exact value, then the fact that this is a mess of nested square roots doesn't bother us. It looks kind of complicated and ugly, but it is still just some number written in terms of square roots and things. So we have, in fact, found an exact value for the sine of pi over 24. We could do the same thing if we were looking for cosine of pi over 24, you know, whatever you want to do here, you can still do the same thing as we were just doing. Now, why is this so powerful of a technique? Well, the reason that this is so powerful of a technique is because you'll notice that essentially what we just did is we showed how we can find sine of pi over 6 times 1/2. That was the pi over 12. And then we did sine of pi over 6 times 1/4. That was the pi over 24. We could keep on going like this, and we could find the sine of pi over 6 times 1 over 2 to the n. for any n by just repeatedly applying these identities. We could similarly find cosine of pi over 6 times 1 over 2 to the n by repeatedly applying these identities. Who cares, right? What does this mean? Well, what this means is we can actually evaluate sine and cosine for angles that become arbitrarily small. Now, that's a weird thing to think about, but the fact that I can, for any given value, I can find a small angle around that value and evaluate the trig functions there turns out to be important, because let's suppose that I need to find an approximation for the sine and cosine at some arbitrary angle up here. Let's call this angle alpha. Well, what I can do is I can write alpha as a sum of very small angles. It's going to be a very long sum, okay? But I can write it as a sum of angles, all of the form pi over 6 times 1 over 2 to the n. And now, I can't necessarily write it exactly this way, but I can come up with some finite sequence of fractions that gets me close enough to this value of alpha by writing that angle as a sum of fractions like this. It's actually very similar to writing something out in binary, if you're familiar with that process in computer sciences. You're essentially coming up with a binary expression for alpha divided by pi over 6. And then what do? Well, then you compute the exact values of the trig functions for that small angle, and then you repeatedly use the sum identity, and you can get an approximate value for literally any angle on the unit circle by using these identities. Now, that is a long process to do, but you can do it. So that is one of the reasons why this is so powerful. Now, fortunately, that is not what you actually do in a calculator when you have to compute the trig functions. It turns out that there are methods from calculus that you can use to approximate the trig functions at any given angle much, much more easily than by using this method. But the point is, you can do it. And because of this, what we end up saying is essentially we can get exact values on a bunch of angles that are arbitrarily close together, because this would give me an exact value if alpha can be written exactly as a finite combination of these fractions. Well, in that case, what we would end up doing is saying that we can find exact values for these trig functions, not approximations, but exact values for angles that are arbitrarily close together. And when that happens, that's really good. It means that as long as this is a well-behaved function, it actually has to behave nicely at all the other points as well. So that's an important feature in calculus. Okay. You don't need to worry too much about what I just said about that stuff if you don't want to. That's mostly for the people who are going to go on to do stuff that is in calculus and actually really even more advanced stuff than just calculus too. But I thought that I should mention why mathematicians care so much about these identities. So make sure that you guys are practicing using these identities. Remember that with the half angle especially, you can end up iterating these identities. And I'm going to stop this here, and let me know if you guys do have any questions, though, about this, because I'm happy to go through more examples with you guys from your homework or whatever in office hours, or we can meet up outside of those.